Hello, I'm Pablo Gómez Abajo. Today I'm going to present our work, seed model synthesis for testing model-based mutation operators. I've done this work with Esther Guerra and Juan de Lara from the Universidad Autónoma de Madrid and with Mercedes Merallo from the Universidad Complutense de Madrid. First, I would like to introduce this presentation explaining what model mutation is. A model mutation is a variation of a seed model by the application of one or more mutation operators, and this process generates a set of mutant models as a result, which contain these variations. Model mutation has many applications, such as model transformation testing, model-based software mutation testing, software product lines testing, the automatic generation of exercises, and the search-based engineering, among others. We can see here at the bottom of the slide an example of a mutation operator applied to the domain of finite automata. The input of the process is the seed model placed on the left, which corresponds to a finite automaton that accepts the even binary numbers. The mutation operator applied in this case swaps the symbols of two transitions. Here we can see two of the generated mutants with these variations presented in red color. These resulting mutants may accept a different language from the one accepted by the seed model. On the right side of the slide we can see another example. In this case it corresponds to the application of mutation operator to the domain of the programming language. In this case the mutation operator modifies an equals operator of a conditional by a distinct operator. The problem we face here, and the problem that motivates this work, is that there is a need to define mutation operators using a simple and compact notation, not the more common general-purpose language, which is error-prone and incurs in high costs when we use it with this target. This language tailored to mutation would enable changing the artifacts in pertinent ways and would also allow testing the mutation operators in an easier way. With this purpose, we have created a DSL for model mutation that we have called WODL. This DSL allows synthesizing models from the WODL programs and testing the mutation operators of them. Here we can see the complete process of our proposal for the engineering of mutation operators. This methodology is independent of the kind of the artifact to be mutated, as the artifacts that we use are models. In step 1, the engineer defines the mutation operators, which are coded in the WODL DSL. In step 2, the engineer validates the defined operators by executing them over the synthesized seed models, and this may lead to detect possible errors in the operators. If the operators are validated, in step 3, the engineer assesses whether more mutation operators are needed. For this purpose, we provide a detailed indication of the degree of coverage of the metamodel by these operators. If this coverage is insufficient, then in step 4, the engineer can use the provided mutation operator synthesizer to automatically generate new operators that increase this coverage, and the process would be repeated. Here we present the main features provided by our WODL DSL for model mutation. This DSL has high-level mutation primitives, it is domain independent, and it is automatically compiled to Java code. The WODL tool provides a set of extensible execution services, such as the mutant validation, the possibility to specify an equivalent mutants detection criteria, a registry of the applied mutation operators, and it is also extensible for post-processing applications. So we can use the generated mutants in other post-processing applications. The WODL tool provides also these two development services, the seed model synthesis that I'm presenting to you today, and a collection of mutation footprints, which is the visualization of the mutation coverage of the metamodel. Well, here we can see at the bottom of the slide an example of a simple water program applied to the simplified BPMN meta model presented in the center of the slide. This simplified BPMN meta model contains the main concepts of the language, such as connecting objects, flow objects, and exclusive, inclusive, or parallel gateways. It also contains two OCL constraints, the invariant placed at the top of the figure, which requires that start events don't have input flows and end events don't have output flows. Also, this constraint requires that flow objects are not connected to themselves. The second constraint, placed at the bottom of the figure, requires that gateways always have input and output flows. At the bottom of the slide, there is an example of a Waddle program. A Waddle program has two parts. The first two lines correspond to the configuration of the Waddle program. In this case, it specifies the mutants are going to be generated in an exhaustive mode. That means that all the possible mutants for the given operators will be generated. Waddle provides another mode to generate the mutants, which is the stochastic mode that generates the mutants randomly. These mutants models will be stored in the out folder, and the seed models will be loaded from the models folder. In the second line, we specify the domain meta model, that in this case is this simplified BPMN meta model shown in the slide. The second part of the Waddle program corresponds to the mutation operators that are going to be applied. In this case, we have included only here one mutation operator, which retypes an event that can be of types start event, intermediate event, or end event as an activity. Here we can see the application of this mutation operator to a simple BPMN model, which is presented here in its concrete syntax. This model describes the process to satisfy someone who is hungry. The process starts when a person becomes hungry. The first activity is to buy the food. Next, the food will be cooked. And then, when the meal is ready, the person eats it, and the process concludes when the person is satisfied. When we applied the previously presented mutation operator, the resulting mutant, the intermediate event meal ready, has been replaced by an equally named activity. Here, the incoming and outgoing references are preserved by the operator. Well, the core of this work is a method to ease the testing of Waddle programs and their operators. So we propose a method based on model finding to automatically produce seed models over which all the instructions of the given Waddle program are applicable, if such models exist in the given search scope. This figure shows the seed model synthesis process. It is based in model search, which is a technique that applies constraint resolution over models, and the model synthesizer works as follows. There is a method to enrich the domain meta model and its OCL constraints with additional OCL invariants derived from the Waddle program. These additional OCL constraints correspond to the requirements that a seed model must fulfill to allow the application of the mutation operators included in the Waddle program. This enriched meta model is loaded into the model finder, and this model finder performs a bounded search of instances of the meta model which satisfy all these OCL constraints. If a model is found, then it is assured that all the Waddle program statements will apply over the generated model when the Waddle program is executed. Okay. So, well, here we present two templates used for these Waddle mutation operators, the object creation and the object deletion. If you would like to consult the templates for the rest of the mutation primitives, you can check them in the paper. Um, the first column shows the conditions to check in natural language, the second column shows the OCL template used in each case, and finally, the third column presents the corresponding OCL code generated for the simplified BPMN meta model example. In the case of the object creation primitive, it is demanded that at least a container reference of the object's type has enough space to store the new object. The derived OCL constraint for the mutation operator create activity for the BPMN meta model checks that there exists at least one business process object which has its elements reference with enough space to store the new object. That in this case means that its contained elements are fewer than its upper bound, that in this case is 10. The object deletion primitive demands the existence of an object with the specified type and feature values, and it requires that it is included in a container reference that would not violate its lower cardinality bound if the object deletion takes place. The derived OCL constraint for the mutation operator remove one activity is presented here and checks that at least one object of the type activity belongs to the business process. This business process object contains other elements apart from this activity. That means that its reference elements has a size greater than 1, that is its lower bound. When we delete the activity, then it is assured that the reference cardinality would still be satisfied. Here we present an example of this seed model synthesis starting from the Waddle program used here as an example during this presentation, followed by the OCL constraints generation and ending with the generated model. In this case, the generated OCL consists of a constraint which requires that the model contains at least one object of types start event, intermediate event, or end event. Then the OCL is loaded into the model finder along with the corresponding OCL of the BPMN meta model, and here we present an example of the generated model. This model has a start event object, then the Waddle program will generate mutants when it is applied over this model. Well, here we present the tool support provided with all these features. Waddle is an open source tool provided as an Eclipse plugin, and it's available at this website. Level 1 shows the Waddle editor, which consists of a complete development environment with enhanced features like syntax highlight, code completion, automated Java code generation, among other features. Level 2 presents the Project Explorer with the set of Waddle programs, the domain meta model, and the seed models used in this example. Here it's shown the corresponding generated mutants, which are stored in hierarchical folders labeled with the name of each mutation operator. Level 3 shows the seed model generator wizard provided, which allows the selection of the number of models to generate, which mutation operators will be used in the process, and it also provides support to include additional OCL code that the seed models will have to fulfill, and it also provides support to start the process from a given seed model. This seed model generator will extend this model with additional constraints to enable the application of the mutation operators included in the Waddle program. Finally, here level 4 shows a representation of the generated model in its graphical concrete syntax. Well, now I'm going to play this short video demo that shows the seed model synthesis execution. This is the model editor, the BPMN meta model, here with all the BPMN meta model classes, the connecting object class here and its social constraints. This editor has code completion and syntax highlight, as we can see here, provided by the tool we used to create this DSL, that is xtest. We can have different Waddle programs in the same Waddle project, and here we are going to generate the specification files for the model finder, okay? That in this case is the use model validator. This dot use and dot properties files will be loaded in the model finder, and they contain all the OCL constraints corresponding to the meta model and the Waddle program. Okay, we can see here the OCL, the generated OCL constraints for this example. And now we are going to launch the seed model generation process from the context menu. Here we specify the different features, like the number of seed models to generate, and the process starts. These seed models will be stored in the models folder along with all the seed models that we have included by hand. Here we have the two generated seed models. This is the first generated model, and this is the second one. Now we are going to apply the Waddle program and see if it works with the generated models. Well, we launch the process and it is generating the mutants that will be stored in the out folder. It is also generating the mutation footprints, and well, it's going to end now. Here we have the generated mutants. It has generated two mutants. This is the first generated mutant, and we can see this seed model and the corresponding mutant. The mutation operator applied in this case was deleting an activity, so we have seen that it has worked. Okay, so to end with the presentation, we have to mention here that we have presented our model-based approach to facilitate the mutation operators testing and their application through their definition in the Waddle DSL and the seed model synthesis. As a future work, we plan to generate near-misses models, which will allow us to generate models where the operators are not applicable, but are close to being applicable. We also plan to generate models which ensure that the execution of the Waddle program will lead to a correct model, and we are currently working on a methodology supporting the integral engineering of mutation operators. Well, many thanks for your attention. Now it is time for you to ask questions if you have any. Thank you very much.